Hi everyone. Thanks for joining me for this talk. It's a real pleasure to have been invited to this workshop on AI for autonomous driving. Now, over the next half hour or so, it'll be my pleasure to talk to you about system-level self-supervision for radar perception and navigation. And by system-level self-supervision, I really mean to talk about how we can leverage adjacent sensing or even entire subsystems to derive a learning signal for particular tasks. And of course, how we might apply that to an increasingly popular sensor such as radar. Now, the work that I'll be presenting today is very much in collaboration with my students Dan Barnes and Rob West. We're all excited about autonomous vehicles and machine learning, of course, otherwise we wouldn't be here. Now, because we have experience with these systems, we know that things like object detection, various other perception systems, semantic segmentation, all that sort of stuff, they do operate, but they also do tend to go wrong. And once we acknowledge that, we very quickly end up in a place where we might think of autonomous driving as fundamentally a systems challenge. The task really is to build systems that are robust enough such that when things go wrong with our machine learning systems, with our inference systems, no bad things happen. Okay, so given that, where does machine learning actually fit in? Well, I've been doing this for a while, and so I've gone back in time to a talk that I gave in 2018 to a similar sort of forum, and I'm delighted to say that many of the things that I talked about back then are still pertinent right now. So typically there are really two places we might look to where machine learning makes a real difference. The first one is on the platform itself, so improving the platform, things like sensor performance, sensor fusion, situational awareness, of course, perception prediction, behavior prediction in particular, or behavior when it comes to planning and so on. The second one is much more offline when it comes to, for example, automatic data generation, when it comes to generally improving tooling. So, for example, versatile simulation systems where you might go from real data into spawning a simulation that represents it, or vice versa, from a simulation into real data in order to, for example, train your systems. And of course, a lot of that is ongoing now, and I'm delighted to see that happen. Much of what I talk about today is very much in the vein of automatic data generation, but also using different systems to really provide that supervisory signal. If we'd met in 2018, I would have talked about two things in particular that we've just done. The first one is on the left here, which is path proposals, where we really have used a system that uses systems engineering, knowledge of systems engineering, as well as ego motion estimation to predict where a human driver might drive in a particular real-world scenario. And on the right here is a system that really uses sensor data and pose information to learn a class agnostic detector, really, of potentially dynamic objects in a scene. So that, of course, is useful when it comes to vision-based ego motion estimation and so on. So once trained, both of these systems can, of course, be deployed effectively using only monocamera at frame rate and beyond. And that's really the essence of why this is useful. The systems engineering in these particular cases provides a learning signal to a capability that is actually then available on the real vehicle. Okay, well, how might we extend this to radar? Well, the first thing that we realize is when people talk about radar, they typically start, have a cold shiver running down their back, because radar is horrible to work with, notoriously so. So we have a whole bunch of sensing artifacts that are present, things like sensor saturation, things like ghost reflections, speckle noise. So even if I tell you where the cars are, without those labels, it might be quite tricky to figure out that these are actually cars. And with that comes the added challenge of seeing what space is free and what space is occluded, of course. And that is very much in contrast to a much crisper sensor, like, for example, a laser scanner that we quite like working with, right? So a particularly interesting question then is, how do we deal with the fact that in radar sensing, getting a high return doesn't always mean it's occupied, and getting a low return doesn't always mean that it's free, right? So how do we deal with that? And I'll talk about that in just a second. So I probably don't have to say much about why radar is useful. Well, it's very complementary to the sensing that we commonly use. It's has a long range, which is great because it allows us to see a long way out, and it's much more resilient to things like different weather conditions, snow, rain, and so on, than, for example, our laser scanners or our cameras are. So that makes it very attractive to use. Why is it interesting if you have a very strong AI and machine learning interest? Well, a whole bunch of reasons. First of all, it's notoriously difficult to interpret, so that makes it a challenge, which is great. Secondly, I've already mentioned that in the previous slide, the noise and artifact characteristics are heterogeneous. They change and are very heavily scene dependent, which is not typically the case with sensors that we tend to deal with. Somehow we need to get rid of these strong sensing artifacts to clean up the data. And of course, radar is also attractive because it partially penetrates through certain objects, right? So that provides an added bonus, but it also provides added challenges in interpreting the data. Given that the sensor itself is so complementary to what we use already, there's of course an increasingly active research field associated with this, and a lot of that also happens here in Oxford, for example, from the mobile robotics group here in the Oxford Robotics Institute, where they look at semantic scene understanding for radar, learned topological place recognition, introspective radar odometry, and so on. But the kind of thing that I really want to talk about today is how we can use learning, and specifically this notion of system-level self-supervision, machines teaching machines, for the interpretation of radar data, for ego motion estimation, and even for a full navigation solution. Okay, so firstly, let's talk about interpretation. And here we might take a very classical sort of inverse sensor modeling approach. But the key ideas really are that in this case, we want to acknowledge that radar data is actually inherently uncertain, and we want to model that explicitly. And in doing that, we want to specifically account for this heteroscedastic, in particular aleatoric uncertainty. Why aleatoric? Well, in the previous slides, I already hinted at the fact that you get sort of confusing, uncertain labels for different radar returns. So high return doesn't necessarily mean it's occupied, and also doesn't necessarily mean it's free. How you interpret it best really depends on the context of the entire scene, and we'll model that here explicitly. Right, so the purpose of this really is to go from a raw radar input, like the one that we see here on the left, to something much more akin to actually an occupancy grid, right? So it's something that as roboticists we're very, very familiar with. And in this occupancy grid, what we really want is the probability of a particular cell being occupied or not. And the key thing that we really want to happen here is we would like detail to be preserved. And we also would like the broad sort of structures of the scene to be preserved, right? And at the same time, we would like to get rid of all the sensing artifacts. And more formally, we might write that down by saying, okay, well, we have a radar scan, which we denote here as X, and we have an occupancy grid, which we denote here as Y, which is basically an element for every cell that we consider. And for each one of those cells, indicated by U and V here, we have a probability of that cell being occupied given the entire radar scan. And that actually is a really important point. For every cell here, Y upper script UV, we consider the entire radar scan. And that is because, of course, of what I said earlier, that the interpretation of that particular cell is very dependent on the entire scene context. Right. Now, how do we actually account for the uncertainty here? Well, we can explicitly do that by introducing a latent variable, right? That is meant to capture the uncertainty in the predictions that we get. So that's this latent variable Z that we have here. And in order to model that specifically, we make an assumption that Z is distributed normally according to some mean and some variance. And the mean and the variance are essentially predicted by a neural network, by a function f that is parameterized by a function by parameters phi. And that is clearly the thing that we see on the right here. And in order to perform inference, we simply, in quotes, marginalize over our latent parameters in order to come up with whether a particular cell in our occupancy grid is occupied, or rather the probability that a particular cell in our occupancy grid is occupied. And so that is what we see at the bottom here. Now, typically that marginalization, this inference step, is intractable, but there are ways of making it tractable, and not only that, there are also ways of making it closed form, which makes it very efficient indeed. The details for that the paper, and I would encourage you to look at that. Okay, so now that we have a formulation, now that we know what kind of inference to perform, we actually need some supervisory signal that allows us to actually learn something about the sensor noise, right? And the idea here is that we let this whole training process be supervised by an auxiliary sensor, and in this particular case it's a 3D laser scanner. So our data set that we see here is now actually a tuple of the original radar scan and an indicator as to whether the laser says something is occupied or free, and of course also whether a particular cell is observable or whether it's occluded, yes or no. So this really provides partial labels for our radar scan. And we can train this whole thing with a variational loss that basically consists of two terms. One, which is a log likelihood term, which really maximizes the probability of the observed labels as derived from the laser scanner. And we only propagate that where labels are available. And the other one is a KL divergence term, which really enforces uncertainty in regions that are unobserved, so in the absence of labels, and we only propagate that when particular regions, or in regions that are actually unobserved. And really that is it. That's the extent of what we need to consider here. And once we sort of have this aligned data of laser and radar, we can throw that at this learning framework, and what we see here is the result at the other end. So on the left here at the top, we see up here, we see the ground truth radar observation. So that's the ground truth occupancy grid we might want. Down here we have the corresponding raw radar data. In the middle we see our approach, and we can see very nicely that detail is preserved. We remain able to see all the cars, for example, that go by. We are able to get rid of many of the sensing artifacts, so it's a much cleaner output that you can absolutely imagine as a pre-processing step for further radar data processing in a more traditional pipelining approach. And importantly, of course, on the right here we see how that might compare to traditional approaches like Cypher, right? And we can see that one problem in Cypher, where you don't make the sort of contextual assumption, where you're saying, well, actually noise is somewhat homogeneous around local neighborhoods, you see that you don't get rid of all the sensing artifacts, and depending on how you set your parameters, you either over smooth, so you lose a lot of the detail, or you just maintain a lot of artifacts, right? So we get rid inherently of all of that. One caveat of this is, of course, that you need to maintain this sort of laser data supervision. That said, of course, that's only during training, that's not during deployment, but also there are ways of getting around that, and that is something for a different conversation. Okay. Next, we really want to talk about ego motion estimation, and while this piece of work has in common with the previous one that you really want to get rid of all the sensing artifacts, what this also provides is a requirement for getting rid of distractors. So while previously you wanted to clean up the scan and keep hold of all the details, including cars and moving objects nearby, here you really would like to get rid of all distracting objects in order to perform basically radar odometry. Okay, and the key idea therefore here is to take a different approach from the one that I've just talked about, and instead learn an artifact and distraction-free radar embedding based on a supervisory signal from ground truth pulse estimation. And we'll talk about how that works in just a second. But another idea here is, of course, to provide an interpretable motion estimate. And by that we mean, let's try and stay as close to a pipeline that you and I as roboticists might recognize, in order that we can figure out where pose estimation part itself might go. Okay, well, let's start with a baseline, right? So this is something that typically we would do as a first draft. So we have a baseline architecture that doesn't really have any learning in it, and it's based on correlative scan matching, because we've used that loads in our community, right? So first we take our polar radar scan, and we convert it into a Cartesian space. That's a fairly standard thing to do. Then we might sample various rotations of one of those scans in order to provide sort of various angle offsets. Then we calculate the cross correlation between each rotated scan and the other radar scan. And in order to do this efficiently, we do that in the Fourier domain. And then we use a weighted sum of the correlation volume to predict our relative pose. So all fairly standard. Now, what we propose to do now here is to actually insert a learning step, because typically this correlation volume will be polluted by all the sensing artifacts that are in the individual scenes. And of course, because they're structure dependent, that sort of noise doesn't just go away. So there's no sort of zero mean noise here. So the question is, can we introduce learning in such a way that we can alleviate that problem while still maintaining the rest of the pipeline? And the answer is yes, we can. So concretely, what we do is again start with the Cartesian the Cartesian radar scans that we have, and now insert a learning step that literally leverages a convolutional neural network to predict a element-wise mask that we then use. So we take that, we multiply that element-wise with the original scan and end up with a feature map. And the idea is that that feature map is now clean of distractions, clean of artifacts, and clean of, ideally, dynamic obstacles or dynamic objects. And once we have that clean feature map, we literally feed that forward into the rest of the pipeline. Now, crucially, the actual pose matching formulation that we've chosen here is fully differentiable, which means that we can explicitly learn a representation in our neural network that allows for distraction-free masks or distraction highlighting masks to be produced, such that we can end up with distraction-free feature maps. And that's important because it literally allows us to have a task-based learning signal that provides this particular space. Right, how do we go about doing this? So to train the system, we use a data collection vehicle that actually has 3 different sensor types. One's a stereo camera, then of course the radar, and a GPS INS system. And here we collect a number of overlapping traversals of the same route. And I'll talk more about that in a second. And of course, those sensors in combination we can use to produce optimized ground truth pose locations across all the collected data, and that we can then learn. Then use as a learning signal. And of course, the data have been collected in various sort of environmental conditions and so on. So again, more on that later. In the paper, there's also a baseline where we use an additional approach that really looks at a multi-session mapping, sort of entropy-based approach to produce masks to really show how learning specifically or task-specific masks via our approach outperforms that. But I'll leave you to look at the paper for that. Important bit is during deployment, we don't need any of the other sensors. We really only use the radar, right? The result then is that we have our raw radar scan on the bottom left here. We produce the mask, so our neural network takes that, produces the mask of things that we really shouldn't pay attention to. That then gets element-wise multiplied with the original radar scan to produce the feature map. And we can see already that that feature map is very clean. There are hardly any artifacts. Hardly any distracting objects like cars that are around us, for example, and then we kind of get that correlation volume. And of course, this whole thing operates at well over real-time speed. I'll say more about that in just a second. But it makes for a very robust matching framework. And you can see how well that works compared to this sort of GPS map that we have here. Where we have these masks that are explicitly optimized for post-prediction, which really reduces the odometry error compared to the current state-of-the-art or the previous state-of-the-art by a factor of 1.5, while operating really an order of magnitude faster, so at 60 Hertz and beyond. And because we've chosen this correlative matching approach, the results that we get are sort of readily interpretable. So we can't necessarily say what's going on in the network itself, so it's not interpretable in that sense. But certainly, if you're a field roboticist and you're out in the field and you're looking at the sort of correlation process that you're running, you can absolutely look at the input to that process and say, oh, okay, well, this is where the errors come from, or this is the behavior that we want. So that is certainly that is certainly helpful. And again, here in these results, you can see that many of the artifacts literally disappear when it comes to the feature maps. Okay, finally, let's talk about a full navigation solution. And here we're really looking at not doing a sort of dense correlation-based matching, but we're looking at learning key points, both for odometry, but also for metric localization, so metric loop closures in radar. And the key idea is, as I said, learning useful key points jointly with learning the corresponding predictors. So here we go. The idea really is to have, again, starting with the raw radar input, a system, which in this case is just a convolutional neural network, that learns three things really. First of all, point locations. Secondly, scores. So how good is a point for a particular motion estimate. And this is really important. We're doing this specifically for motion estimation. And of course, a descriptor that allows us to find similar points or match similar points across two different scans. And the location part is really important here, of course, because we hope to be localized to real-world objects rather than sensor noise. And we hope that the points are also located really on static elements in order to allow us to estimate ego motion, such as walls and buildings and so on. Okay, so for the purposes of motion estimation, we kind of look at two proximal scans, so scans that are taken nearby, and we basically have the architecture, which is a convolutional neural network that maps to point scores and descriptors for each one of the scans that we're considering. We bring those forward into a key point matcher that compares the individual descriptors that have been computed, and then that goes into a pose estimator that finally predicts the actual transform between the individual radar scans. Now, importantly, both the key point matcher and the pose estimator are differentiable, right? So that means, just like before, we can use some form of ground truth signal of relative pose to train our neural networks, and that is again very, very important in order to make this work. And I think you can see where this is going in terms of how we end up with a trained system, in that we use ground truth pose estimation to do this. Importantly though, what we can do is not just use this for radar odometry, so proximal scans, but the idea here is that we can use the same system to also provide basically metric loop closing, right? So metrics of localization. So we can use the same framework for metric localization by combining all the individual key point descriptors in a particular scene. So for example, by max pooling into what is a scene embedding or a location embedding, as mentioned here on the slide. And we can then take that from two scans and compute the cosine similarity, for example, between these two location embeddings to end up with a matching of scenes that are not proximal, that can be far apart, but matching of scenes against each other. And of course, once we have that, we can use the same framework as per the previous slide, where we look at radar odometry to solve for a metric loop closer, so a pose estimate into that scene. And because all of that is fully differentiable, again, we can leverage the same data set that I've talked about previously, and we'll talk about again in a couple of minutes, where we have three different sensors that allow us to provide pose optimization. So we end up with ground truth poses but that are ideally suited really for our application. And during deployment, again, we only really deploy with a vehicle that has a radar on it, so we only really need that particular radar. We then deploy our model forward to provide point locations and scores and descriptors for that. And if we look at those points projected into 3D, we can see that indeed all of these points reliably detect static elements in the world, such as walls and buildings. So that feels like a win. But we can actually do more than that, in the sense that we can look qualitatively at what those matched points actually look like. So in the stationary sense, all those points are matched across scenes quite well. The only point that is slightly offset there is one belonging to an actual car moving through the scene. But as we start moving forward, we can see that the point matches, or this point correspondences, are consistent with the motion of the vehicle. So as we go forward, as we go through a slight bend, and as we go through a tight turn. And that becomes also even more clear when we look at a video of this. So again, we can see here that most of the points that are detected and matched belong to or fall on walls and buildings. Again, here we can see how this works as we go from moving forward through a tight bend and back again, all with accurate key point detections and accurate odometry estimation. And of course, we can replicate that throughout the entire data set. So this is not a hand-picked example. We can look at various different places with very complex motions. And again, we can see that this is consistent across the entire data set. Finally, of course, we can use this for metric localization, where we can take various different traversals. We can run the loop closure across the individual trajectories, and we can use that to perform graph optimization to actually come up with an optimized, map of the entire trajectory traversed, and of the entire environment that we traverse. So not only is that resulting map globally consistent, but the inference that we use here runs at well over real-time speeds. Okay, so for this part then, what we've got is a key point learning system that really predicts the point locations, the scores, and the descriptors from pose information alone. So the key trick here is, again, the system is self-supervised by the ground truth pose estimate that comes from a different subsystem. And the result here is really a fully fledged and very robust and accurate radar navigation system that runs at over 30 Hertz, so well beyond real time. And another thing to note here is that the architecture that we propose here is actually sensor agnostic. So we deploy that in the context of radar, but when Dan first thought of this particular approach to it, what we had in mind is something that runs on radar, but also on vision and other modalities. Though we don't show that here. Okay, I hope I've convinced you that there's some really useful things we can do if we consider this notion of self-supervision, particularly with systems that provide ground truth pose estimates in the context of radar data processing, not just when it comes to interpretation, so having something that cleans up your data, maybe ahead of inserting it into a more standard processing pipeline, but also in terms of radar odometry, ego motion estimation, and a fully fledged navigation system. Now, if you find that interesting and you would like to get started with radar yourself, then I've got something else for you, which is the entirety of the data that we've used to train all of the approaches that I've talked about today, which is known as the Oxford Radar Robot Car Dataset, which we have released a couple of months ago on the ORI website that you can see at the bottom here. And in there are about 32 repeated traversals of city driving, over 280 kilometers of it, and importantly, it has, of course, everything you might expect: LiDAR, vision, GPS, INS, as well as the optimized poses. But also importantly, it's got the associated radar data. So feel free to download it, have a play, get started, contribute. So that would be great. There are many other things that I would love to talk about, but I don't really have time to talk about. But one thing I'd like to give you a heads up for in terms of what's next is how we might use radar, particularly when it comes to training our systems based on simulation, right? So here you might you see a Kala simulation, but one thing that we've been working on is how you translate these scenes into realistic radar data that you can then do other stuff with. I hope to be able to talk to you about that in the next few months, really. It should be released soon. All right, good. I'll leave you with that. Thank you very much for your attention, and I hope you enjoy what's left of the workshop, and hopefully we'll catch up at another venue, either virtually or in person. Thank you very much. Bye-bye.